Okay, in this second episode of Guide Sheet number 5, we're going to go ahead and apply the law of acceleration by using free body diagrams to help us out for situations where we have different forces acting on an object. So we're going to start here with object A. It seems to be in a position where the only force that we're concerned with affecting it is its weight, the force of gravity. That would indicate it's not on any surfaces. That would indicate that it's going to be accelerating downward. Now, if it's currently at rest, that means it's going to start to speed up as it falls. If it's currently moving, again, it's still going to speed up as it falls, but it will have started from some initial velocity. Now, the general law is that when we add up all the forces, this is the law of acceleration, when we add up all the forces, we get the net force. So it's also known as the net force. Those two things are equivalent to each other. That will be equal to the mass of the object multiplied by its acceleration. Again, acceleration is a vector, so therefore net force is also a vector. So direction is important. Now, we can't necessarily just jump right in and solve the equation. We have to make sure we know what the net force is from the free body diagram. In this first one, the net force, the only force, is 600 newtons. Now that's pointed down, so it's 600 newtons. It's pointed down. Now if we're going to apply the second law, the law of acceleration, we also are going to need to know the mass of the object. Now for all of these, we're going to assume they're on the Earth. The Earth has a acceleration rate at its surface of 10 newtons for every force field of 10 newtons for every kilogram of mass. So if we want to know the mass of an object here on the Earth, if we take its weight in newtons and we divide it by 10 newtons per kilogram, the weight being in newtons, these newtons would cancel out and the kilograms move to the top, and we will have the mass in kilograms. So 600 newtons divided by 10, 10 is a nice easy number. It's actually 9.8, and it varies a little bit based on what position on the Earth you are. 9.81 is kind of an accepted average. But for our purposes, we're rounding that off to 10. It's not totally accurate, but it makes the numbers easy to work with. And we're really working here with the concept more than the precise numbers. So that's going to be 60 kilograms. Don't forget our old friend McWin, good Irishman. Mick means mass is in kilograms, and weight, which is the force of gravity, is in, I should make that capital, is in newtons. Okay. Now the acceleration, if F equals ma, then A is equal to the net force divided by the mass. And the direction will be, they are directly proportional, so the direction will be the same as the net force. So 600 divided by 60 is 10, that's interesting, meters per second, and down. Notice since this thing is falling, it's in free fall, the only force acting upon it is gravity, then the acceleration is the same as the Earth's gravitational field strength. 10 newtons per kilogram means that when you drop a mass, it will accelerate at the rate of 10 meters per second if weight is the only significant force acting upon it. Alright, so let's look at some situations where weight's not the only force. In B, now we have a upward force of 400 and a downward force of 600. So 600 minus 400 leaves us with a net force of 200 newtons, and the overall direction is down, more down than up. The mass, it's the same 600 newtons that we had before, so that's again going to be 60 kilograms. And now when we find the acceleration, we're going to want to take the force, 200, and divide by the mass, 60, and we get 3 1/3. We can just round that to 3.3 meters per second. And that is also down. Again, these two must match. The by the second law, the net force and the acceleration are directly proportional to each other. That means not only must they impact each other the same, they must also be in the same direction. Notice this time we had some air resistance, so that reduced our overall acceleration, which means this thing will not be picking up speed as much as our first case was. Okay, if you look at these, if you've gotten a sense of how free body diagrams work so far, you should notice that these are different from the first two in that they have an additional normal force. Now, normal forces are caused by surfaces in contact, so it indicates that these objects are on some kind of level surface. And normal means perpendicular. So if the normal force is pointed this way, then the surface must be at a right angle to that force. Your thumb and your first finger make a nice little perpendicular. So if you're ever trying to figure out which way a normal force acts, just point your finger in the direction of the surface, and then your thumb will naturally point in the direction of the normal force. Okay, so in this one, 8,000 down, 8,000 up cancel each other out. That means the leftover force is 2,000 newtons worth of friction, and that's to the left. Now for the mass, we're going to divide this by 10, divide the weight by 10 here on the surface of the Earth, and we have 800 kilograms. Then for the acceleration, we're going to take the force divided by the mass, 2,000 newtons. We're going to divide that by 800 kilograms. We're going to get 2.5 meters per second, and that's to the left. Now, something to be careful about. The free body diagram does not tell us the current state of motion. It just tells us the change of that motion. So we do not know if this thing is moving to the left. In fact, with friction being the force that generally works against motion, I would be assuming that this thing was moving to the right and slowing down as it moved to the right. Okay, but the diagram does not tell us that directly. Okay, the next one, the only change we've made is essentially to double the overall net force. From our previous work in Guidesheet number 4, if we double the overall net force, we will essentially double the rate of acceleration. It's going to be 4,000 divided by 800. Zeros cancel out. 40 divided by 8, that is 5. It's also, again, going to have to be to the left. So doubling the net force will double the rate of acceleration if you change nothing else. Okay, now this time we're going to add an additional force. Not only do we have friction, we also have some kind of applied force. Perhaps a person pushing or pulling on the object to move it across the surface. All that means is now we have to deal with the difference between the two horizontal forces. Again, the normal force and the gravitational force on a level surface without any other forces at angles, these two will just cancel each other out. So to find the net force, it's 22 newtons to the right minus 14 newtons to the left. 22 minus 14 is 8 newtons. It's overall to the right, more to the right than to the left. The mass again will be 20 divided by 10, which is 2 kilograms. The acceleration will be the force, net force, 8 newtons, divided by 2 kilograms, and that's 4 meters per second. So we'll speed up at the rate of 4 meters per second for every second that we move. And again, the directions must match. Okay, and our next one, and our last one, is 44 and 28. And we've also seen an increase in the weight of the object, which means also an increase in its mass. Now that does not mean the second object is larger physically. It means it has more stuff. Size is not a direct measure of mass. It depends on how many molecules the object is made of. Again, for net force, we're going to take 44 newtons. We're going to subtract away 28 newtons. That's going to give us a total of 16 newtons. Now, we have doubled the force on the object, the net force from the first time, from letter E here. It's still to the right. Now, that would at first make you think that we're going to have twice as much acceleration. But we should notice something else. The force of gravity, the weight, is 40 newtons. 40 divided by 10 means we now have made the object twice as massive. Now, Newton's law of acceleration says the acceleration is directly proportional to the net force. Now, I have doubled the net force, but it's also inversely proportional to the mass. And I've I've increased the mass by 2 as well. So those two are going to end up counterbalancing each other, and we take 16 newtons divided by 4, and we get exactly the same 4 meters per second to the right that we had before. So again, it's more than just the force. It's a relationship between force and mass. And it's not just any individual force. I wasn't concerned about each individual force. I was looking at the total force when I added them all together. 40 newtons up plus a negative 40 newtons down cancels to 0. 44 minus 28 leaves me to 16 total left over. The direction's to the right. I divide that by the mass. I get the value of the acceleration. Okay, so that's we're starting to put a lot of stuff together there. If you're having trouble with any of this, come see me. We'll look specifically at some examples and try to help you out.